Now we want to talk about not just step functions, but more complicated functions that have jump discontinuities. And here's a way we can take advantage of the basic step functions in order to kind of represent and then eventually take the Laplace transform of other functions that have jump discontinuities. So let's say we start with a function y equals g of t, whose graph looks something like this. Here's t, here's our y-axis, and this is the graph of y equals g of t. How can I represent the function that's 0 until you get to c, and then looks just like g of t shifted over by c units? In other words, the graph would look just like this. Just as a technical detail, we'll say it starts like that. So here's the y-axis. What would be a formula for this function? Well, it's 0 until you get to c. So we're going to start by writing u sub c of t times something. That will guarantee it's 0 until c. Now u sub t is 1 after that. I want something that looks just like g did here, but this is now shifted over to the right by c units. And we get that by just writing here g of t minus c. Because g of the value here, g of c minus c, is g of 0. That would be what we get here. And then this would just copy the behavior over here. So we can represent functions like this just as a product of a step function and a shifted version of our original function. Now here's a question. Do we have any way of computing the Laplace transform of things that look like this? And the good news is, of course, yes, we do. Here's the theorem. It says if capital F of s is the Laplace transform of little f of t, if this Laplace transform exists, and remember it certainly will exist if f itself is piecewise continuous on any interval and doesn't grow too fast. And so if this Laplace transform exists for s greater than a, and if c is a positive constant, then we can take the Laplace transform of u sub c of t times f of t minus c, this type of thing that we were looking at here, and that will just be e to the minus cs times the original Laplace transform of little f, that's capital F of s. So the Laplace transform of this kind of shifted function is just e to the minus cs times the Laplace transform of our original function. And just as an immediate consequence of that theorem, if we want to take the inverse Laplace transform of e to this minus cs times some capital F of s, well, that's just tells you just use this step function u sub c of t times the inverse Laplace transform of capital F. But the one trick is you have to remember that you don't just take the inverse Laplace transform of capital F itself. That would be little f of t. You have to use a shifted version of it, little f of t minus c. So that's the only kind of thing to be really careful of. Let's look at a simple example. Let's say I want to start with a very simple function. Here we have f of t is 1 minus t when t goes from 0 to 1, but then I want it to be 0 after that. How am I going to create a nice formula for, well, I won't write it like that. I'll write here y equals f of t, and I want its graph to look like this, to be equal to 1 minus t just between 0 and 1. I don't want it to continue down like this. I want it to be 0 after that. So I just want it to have non-zero values between 0 and 1 and then stay 0. Of course, I could write it by just saying it has the value 1 minus t between 0 and 1 and it has the value 0 afterwards. But instead I would like to write it in a manner that will make it easy for me to compute the Laplace transform of later. Here's a neat way to do that. I could write it as 1 minus t everywhere, which would look like this. And then in order to zero it out after we get to 1, I would want to add 1 minus t back, beginning at t equals 1. In other words, I want to make this part go away. So I'm just kind of showing you visually what my thoughts are. I'll write down y equals 1 minus t, or sorry, not y, f of t equals 1 minus t. I keep forgetting I shouldn't cross things out like that. I can just erase them here easily. F of t is 1 minus t plus beginning at 1, so I write u sub 1 of t to say what happens at 1. I'm going to add back in 1 minus t. But this thing that I'm adding back in, that looks like 1 minus, I'm sorry, I'm not going to add 1 minus t, I'm going to add the opposite here, t minus 1. That's what I meant to say here. Why does this work? Well, between 0 and 1, this term is 0, and so f of t is just 1 minus t. And after, from t equals 1 on, this term here, the u sub t, is just 1, so I get 1 minus t plus t minus 1, and that ends up being 0. So this is my entire function, f. Let me erase all of this stuff here. And this function f is the one with the graph shown above. And let me talk about now writing a different function. I'm going to draw the graph of a new function, g of t, and I would like it to look like this. Let's say it looks like 1 minus t, just like f above, but then it goes and does the same thing again like that. And then it's 0 afterwards. Of course, you should be able to see how you could modify it to produce a triangular wave function that continues. How would we create a function like this? Well, before we do that, let me do a side function here. This is what So first let's look over on the side and ask, how do we get a formula for the function whose graph looks like this? And then we'll use that to help us find what we want in the end. Here I would like a function which is 0 up until 1, and after that it looks just like f of t, going from 1 here down to 0. This is now at 2, and staying 0 after that. Well, the graph of this function here, this curve here, looks just like the curve over here, only shifted to the right by 1 unit. So this is exactly y equals u sub 1 of t times f of, not f of t, but f of t minus 1, because it's this function f shifted by 1 unit. And how does that work? Well, the f of t is given by this formula over here, so this is just y equals u sub 1 of t times f of t minus 1. We replace t by t minus 1. We have 1 minus t minus 1. Then we have to add this u sub 1 of t times, u sub 1 of t minus 1 times t minus 1, which is t minus 2. Let me rewrite that, I'm sorry. Times t minus 2. There we go. I know this is, my planning wasn't as good as it should have been here. Let's take a look. This is equal to u sub 1 times 2 minus t, u sub 1 of t times 2 minus t. That's this first term here. And then we have u sub 1 of t times u sub 1 of t minus 1. Well, what is u sub 1 of t minus 1? U sub 1 of t minus 1 is just the same as u sub 2. because it's just like u sub 1 shifted over to the right. So this is u sub 1 of t times u sub 2 of t times t minus 2. Now u sub 1 times u sub 2 is just exactly the same as u sub 2, because u sub 1 is 0 until 1, u sub 2 is 0 all the way until 2, and then after 2, this is exactly 1. So this is just u sub 1 of t times 2 minus t plus u sub 2 of t times t minus 2. Now let's look at how we could represent this function y equals g of t, whose graph looks like this. There's 1, there's 2, it goes to a height of 1 here. This function g of t is just exactly f of t plus the function over here to the right, which is u sub 1 of t times 2 minus t plus u sub 2 of t times t minus 2. And of course we put in what f of t is. This is 1 minus t plus u sub 1 of t times t minus 1 plus u sub 1 of t times 2 minus t plus u sub 2 of t times t minus 2. And that's just 1 minus t plus u sub 1 of t. The t's here cancel. We just get u sub 1 of t times 1 plus u sub 2 of t times t minus 2, which we probably could have figured out in a simpler way, but I wanted to go through these steps to show you the different pieces here. So what is g of t? It's 1 minus t plus u sub 1 of t plus u sub 2 of t times t minus 2. You can see that that makes sense. Between 0 and 1, we just get 1 minus t, which is what we want. Between 1 and 2, this adds 1, so we just have 2 minus t, which would be like this. So this is exactly t minus 2 between 1 and 2. And then after t equals 2, this is t minus 2, and we're adding, this is 2 minus t, and then we're adding u sub 2 of t times t minus 2. That will cancel things out exactly after t equals 2. To finish things up, we would like to compute the Laplace transform of the function we were just talking about. That was the function g of t equals 1 minus t plus u1 of t plus u2 of t times t minus 2. What would be the Laplace transform of g of t? Well, again, by linearity, we can just take the Laplace transform of each piece. The Laplace transform of 1 is just 1 over s. The Laplace transform of t is just 1 over s squared. The Laplace transform of u1 of t, we've already seen, is e to the minus 1 times s over s. And finally, how do we take the Laplace transform of u sub 2 of t times t minus 2? This is just a shifted version of the function t, shifted by 2. So we just take the Laplace transform of t, which is 1 over s squared, and we multiply it by e to the minus 2s, like that. And there we have it. That full thing is the Laplace transform of g of t.